Hello and welcome. We live in a world that is literally built from stuff: steel, concrete, plastic, you name it. But have you ever stopped to wonder how we know it won't fail? Today, we are going to uncover the secret lives of these materials, and we're going to reveal the hidden strengths that, well, keep our world standing. And it all kicks off with one simple but really crucial question. I mean, how do we trust a skyscraper not to sway too much in the wind? Or a bridge to actually hold up thousands of cars every single day? Or, a plane to fly safely through some rough turbulence? The answer isn't just hope or, some good guesswork. It's science. And it all comes down to finding the answer in a lab. And this is exactly how we find it. We take a small piece of a material and, using a machine like this one, a universal testing machine, we basically interrogate it. We push it, we pull it, we stretch it, until it finally fails. Because by understanding how it breaks in the lab, we can make absolutely sure it never ever does in the real world. All right, so let's start with the most common and honestly the most fundamental test of them all, the static tension test. You can think of it as the ultimate stretch test, where we literally pull a material apart with a slowly increasing force just to see what it's really made of. Okay, this right here is our test subject, a standard piece of mild steel, and it's locked into the grips of the testing machine. We are going to follow this little piece of metal on its entire journey, from being strong and stable all the way to its final breaking point. And along the way, believe me, it's going to tell us everything we need to know. So first, as we start to pull on it, the steel enters what we call its elastic phase. Just think of a rubber band, right? You can stretch it out, and when you let go, it snaps right back to its original shape. That's elasticity. The material changes shape, but the key is that change is totally temporary. But if you pull hard enough, something changes. The material enters its plastic phase. Now, instead of a rubber band, think of a paper clip. When you bend it, it stays bent. The deformation is permanent. This is plasticity. It's the ability to change shape for good, without actually breaking apart. So, this difference is absolutely crucial to understand. Elastic deformation is temporary. It bounces back, just like that rubber band. Plastic deformation, on the other hand, is permanent. It stays deformed, like the bent paperclip. For any engineer, finding the line between these two behaviors, well, that's one of the most important things you can do. It's the point of no return. Now, as we're stretching this piece of steel, the machine is recording every single moment. It's plotting the force we apply against how much the material is stretching. And the result is a graph, sure, but it's so much more than that. It is the material's entire life story, told in a single curve. And here it is. This is the stress-strain diagram. Let's break it down. On the vertical axis, you've got stress. That's the force we're applying. And on the horizontal axis, you've got strain. That's just how much the steel is stretching. But please, don't just see this as boring data. See it for what it is, the dramatic story of our steel specimen's struggle. Okay, let's follow the plot. From the very beginning, at point O all the way up to point A, the line is perfectly straight. This is the elastic range. In here, stress and strain are proportional. If we were to stop pulling anywhere in this zone, our steel gar would snap right back to its original length, completely unharmed. No problem. But if we push past that, we hit point B, the yield point. And this is the moment the story takes a turn. This is the elastic limit. It's that point of no return we talked about. Any stretching that happens beyond this point is now permanent. The steel's internal atomic structure has literally started to shift and slide in a way it just can't recover from. Now, this is where it gets really interesting. Even after it starts deforming for good, the steel actually gets stronger for a little while. We call this strain hardening. The curve keeps rising until it hits its climax at point E. This is the ultimate stress. It's the absolute maximum load the material can possibly handle before things start to go downhill fast. So why does the graph start to slope down after hitting that peak? Well, it's because the material is starting to lose its battle. All of the damage starts to concentrate in one weak spot, and the bar begins to neck. It thins out dramatically, just like you can see here. Since the area shrinks, it just can't hold as much load anymore. And now we reach the final act. As the necking continues, the stress needed to keep stretching the bar drops and drops until we hit point F, rupture. The specimen fractures, it breaks in two, and our test is over. The material's story has come to its very dramatic end.
But look at that whole journey from the yield point all the way to the final break. That long, drawn-out stretch is an incredible property called ductility. It's what allows steel to bend and deform and give us all these warning signs before it just fails catastrophically. A brittle material, by contrast, would just snap with no warning. Ductility is what makes steels so unbelievably safe and useful. So a stretch test tells us a whole lot, but it's not the complete picture. To really get a sense of a material, we need to ask some different questions, like how does it handle being sliced, or maybe even just dented?
So this is a shear test. Instead of pulling a material apart, shear forces try to slide one part of the material past another. Think about the force on a bolt or a rivet that's holding two metal plates together. We have to test this to make sure those connections don't just get sliced in half under pressure.
And what about just resisting damage on the surface? I mean, we don't want materials that dent or scratch easily, right? That property is called hardness, and it's all about a material's resistance to getting a permanent dent right on its surface.
You know, the test for hardness is beautifully simple. You just take a very, very hard object, like a little steel ball or even a tiny diamond pyramid, and you press it into the material's surface with a very specific amount of force. Then you just measure the size of the dent it left behind. A smaller dent means a harder material. It's a super quick, non-destructive way to check for quality. So we've stretched, we've sheared, and we've dented these materials in a controlled lab setting. But what's the point of all this? How does this story, written on a graph or a tiny little dent on a metal block, actually translate to the world that we all live in? Well, it matters because these tests are the absolute foundation of modern engineering. They provide the hard data that tells designers the safe limits for every single component. This knowledge is what ensures our buildings and bridges are safe, it's what allows us to design lighter, more efficient cars and planes, and it guarantees that the materials being used meet the exact specs they're supposed to. Every single test tells a story that keeps us safe. So go ahead, take a look around you right now. The metal in your chair, the concrete in the walls, maybe the glass in the screen you're watching this on. Every single one of them has a story. A story of strength, of elasticity, of limits that was discovered in a lab. So, what hidden story is the material nearest to you telling right now? Thanks for joining me.